All right, so we're going to jump into Chapter 8, and only 2 sections in Chapter 8, but just like Chapter 7, small chapter, but very important stuff, very important concepts. So 8.1, we're going to be talking about the sample mean distribution. Okay, so the first paragraph here, the first little section of Chapter 8 is a really good overview of what we're talking about, and I would advise you guys to read that, and I'll go ahead and try and summarize it for you as well. So, okay. So over here, the first section here. So suppose the government wanted to find the mean income of all U.S. households, right? So we're talking about trying to find a population mean. So that's one of the things we're going to want to remember, our notation. So the mu, remember, is the population mean. And then X bar is the sample mean, right? Because the government's probably not going to go out and find everybody's income and take the actual average. They're going to take a sample. And so this is saying that suppose they randomly select 250,000 households, and they get a sample mean. They get a sample mean of 72,641. Okay, so that's the X bar, right? That's the sample mean. It's not necessarily the population mean, but it's the mean they got from their sample. Now, obviously, if somebody else does the same study, samples 250,000 randomly selected households, because they're randomly selecting, they probably don't get the exact same people, right? So they might get a different average. So that's where it says, okay, maybe a second random sample got an average of 71,849. So a different number, right? And a third one would get a different number. And so this idea is that because the sample's being randomly selected, then the sample mean we're getting each time we do it is also going to vary from sample to sample. It's going to change. And so that actually makes it a random variable, which means we can have a distribution for it. So the book and the notation for this will be, it's kind of like putting these two things together. So it's like mu and then a subscript of X bar. So this is going to be our sample distribution. Sample mean. We got to distinguish here. So sample mean distribution. Okay, so there's a definition part over here. The sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from sample size n. And then the sampling distribution of the sample mean. X bar is the probability distribution of all possible random variables, so all possible averages. So that's the idea. And basically, this idea, I'm going to start summarizing all this stuff, trying to simplify it. The idea here is that if we keep taking samples of the same size and we repeat it over and over again, we will get a normally distributed sample mean distribution. Okay, so this would be our sample mean. And the idea is, let's think about this with an example. If we wanted to know the average let's say, height of students in the high school. Obviously, we're not going to go out and measure everybody. We're going to select a sample. So let's say I give this to you guys as a project, and I say, okay, so go out and sample 30 students and find their average height. Each one of you are going to randomly select different people to ask, and so each one of you are going to have a different average. That's the idea of this distribution, okay? The most amount of you, though, will have a average that is really close to the actual average of the students in the high school. Some of you, just based on randomness, right, might have just happened to select people that tended to be shorter. So you may be over here, but not a lot of you, right? So that's why it's low here. Some of you might randomly have selected a lot of people that are tall. So again, that's not a lot, but over here. But the majority of people are going to be right here, close to where we think the actual population average would be. And this is basically the whole idea of statistics, right? Taking samples and finding the actual population parameter. So this idea is that if I didn't use the number 30, right? If I told you to go out and sample 2 people, what do you think that would look like compared to sampling 30 people? Do you think we would be closer to the actual average or further away from the actual average? So this is the idea called, and I'm skipping down a lot of this, but I'll come back to it. This is an idea called the central limit theorem, right? And I think it's something we've talked about before. If the sample size increases, we get closer and closer to the actual population parameter. So the idea here is, because we're not talking about individual data points anymore, because we're talking about a sample distribution, right? Each one of these data points, in my example of sampling 30 people, each one of these data points is an average of 30 people, right? So what's going to happen is, as that sample size increases, we get closer and closer. So as the sample size increases, and remember what we use for sample size is n. So as n increases, the sample distribution, the sample mean, gets closer and closer to the population mean, right? We get closer and closer to that actual value, the one that we're looking for. So that's the central limit theorem. And we use this idea as well theorem. We use this idea as well to talk about increasing the number of samples we take, right? So if I had a statistics class of 8 students and I have them go out and sample 4 people each, and they each come back with an average and I get a distribution, that's one way of doing it. But compare that to a class more like ours, let's say 25 kids, and each one of you are going out and getting 30 random samples, random individuals, a sample size of 30. We're going to get closer and closer to an actual distribution. In fact, with low n values, we might still see a normal distribution, but with high n values, with a higher sample size, we might see, again, a normal distribution, but it's all really close. It's all centered really close to that actual population parameter. Okay? I used the number 30 before. That is kind of like a standard value. If we don't know what the actual population distribution looks like or anything like that, 30 is kind of like a normal, typical number to choose for a sample distribution to become a normal distribution. And the idea is, like with the difference here, is that the parameter is equal to the sample mean, okay? Because if we have a large enough sample, we can assume that the sample mean is equal to the population mean. And then the idea here is that the sample standard deviation is not necessarily going to be actually just equal to the population standard deviation. It's actually going to be a lot smaller based on our sample size. And so we take the population standard deviation and we divide by the square root of n. And that gives us this idea of a much narrower distribution centered closer to the mean. Because if we have low n values, if we're taking small sample sizes, we're going to get averages that are spread out. It's more likely, in my example, that you're going to pick, like, if I only told you get 4 people, you might end up with 4 people that are typically shorter than average, right? Or you might get people that are typically taller than average. But if I go out and tell you to get 30 people, the average of all those 30 people are going to converge into the middle. They're going to get closer and closer to that center of the distribution. And so it kind of like squishes the distribution in. And so this is our formula for finding the sample standard deviation. So that's sample standard deviation. Okay, so that's one to remember. That's what we'll be using. And this idea as well, because of the central limit theorem, we're going to say that the sample mean is equal to the population mean. Okay, so going down into the book, they also call this sample standard deviation. Here they call it the standard error of the mean. Standard error. They might use other terminologies for it. And you can see, so for example, let's say there's a simple random sample of size n equals 9, and the population average is 100, right? The sampling distribution has a mean of 100. Then the standard deviation of the sample distribution, they give this information somewhere else. If the population has a standard deviation of 15, then we would be doing 15 divided by the square root of 9. And so we'd have a sample standard deviation of 5. Okay? If we increase that sample size to 25 using the same population, now our sample distribution has a standard deviation of 3, right? And so here's a good visual of that, right? You have a population parameters with mu and sigma, and then you have your sample mean distribution. And it's centered at that same place. Both have the same average of 100, but as that sample size increases, it kind of squishes into the middle, right? It's a nice way of thinking about it. So the idea here is that because it's a normal distribution, we can use the same calculator methods that we used in Chapter 7 for the normal distribution. So we're going to be using normal CDF and inverse norm. So it's pretty much the exact same thing. The main difference with the sample is this. Okay, that's the main difference. This isn't a difference, but it's just something we're going to have to know because it might not give us x bar, it might give us mu. We just have to know it's the same value. And it's probably going to give us sigma. And we have to know that we have to divide that by the square root of n in our calculator. So, for example, if I bring out the calculator here, let's see if they have an example. Well, let's do this. So let's make up my own. Using the same numbers they have, let's say we have a population that has a average of 100 and a standard deviation of 15. And we're going to take sample size of, let's say, 16. So we're sampling 16 people. What is the probability? So what is the probability that the sample average of the 16 people we choose, what's the probability that that sample average is, let's say, less than 97? Okay, so we know that the actual average is 100, the actual standard deviation is 15. I want to know the probability that when I take a sample of 16, I get some average that's less than 97. So this is a very similar question to what we were doing in Chapter 7. So I'm going to draw a curve. Okay, and I know that this is centered at 100. And I'm talking about less than 97, so I'm going to put 97 kind of where it would be. And I'm looking at this shaded area. So now I'm going to go to the calculator, and I'm going to go to my distribution, so second vars, and I'm going to do normal CDF, and I'm looking for my shaded area. So the lower bound, it's kind of unbounded to the left, so negative 99999, and my upper bound is going to be that 97. My average is 100. And here is where we have to remember the difference that we're now using a sample distribution. So we have to put in 15 divided by the square root of n, which is 16. Right? Or we could do this work ahead of time and put in an actual number there. But we can also just plug it in like this. So I choose to do that because if I make an error in my calculation, this just takes that step away. So I go ahead and hit that, and the answer to the question I just kind of made up is approximately 21.2%. So what's the probability that the sample average, when sampling 16 people, is less than 97? It's 21.2%. What do you think is going to happen if I take this same situation and I make an 100 people? So same situation, but now I have 100 people that I'm sampling. What do you think is going to happen to that probability? Same question. So if I'm sampling more people, this distribution becomes squished in, right? And so now when I think about 197, this area is going to be much smaller because we've been smushed in, right? So I'm expecting this probability to go down because, again, if we're sampling 100 people, we're probably going to be a lot closer to 100 than we were in this previous distribution. That's kind of like what this whole section is about. So I'm going to go ahead and calculate this. So it's the same setup, right? Left is unbounded. 97 is my upper bound. I have a mu of 100. Well, my sigma is now 15 divided by the square root of 100. And if I answer that question, I get approximately 2.3%. Right, and so we got a pretty big jump from 21.2% chance of getting an average that's less than 97 to a 2.3% chance that the x-bar, that the average is less than 97, because we're sampling a lot more people. So I hope that makes sense to you guys. And really, that is the book goes into simulations and using technology to do like hundreds of simulations at a time, but we don't have that technology. We're not going to do that right now. Here is that central limit theorem as well. Oh, let me get that out of the way. Here's the central limit theorem as well. It talks about the fact that it doesn't matter what the population distribution looks like. If the sample mean distribution will always approach a normal distribution. So it can be a uniform distribution, but when we take sample distributions, we get a normal distribution. It can be skewed to the right, but as long as we're taking sample distributions, it's going to approach a normal distribution, right? So that's just showing the actual population distribution here. In A, it's definitely skewed to the right. And then in B, this is now the distribution with a sample mean of sample means with n equals 4, right? Just sampling 4 people, finding the averages, and putting them into a distribution. It's still looking skewed to the right. Now with n equals 10, it's got some outliers here on the right, but it's getting really close. And then by 25, it's a normal distribution. So that's that. Also, that idea where the 30 is kind of like a go-to number, where once you've gotten to 30 at least, you'll know that it's almost a perfect normal distribution. So that's about it for 8.1, and I will see you guys in the next one.